Hello everyone, welcome to the third lecture of reinforced concrete structure. Before starting this lecture, let's take a look what we have covered in second lecture. In second lecture, we have covered some more basic concepts for structural designing. First, we have learned about different types of loads, and knowledge of these loads will improve your design skills. Then design philosophy, where I describe three design philosophies. Working stress method, it is based on linear elastic theory, where we assume that both concrete and steel behave in linear elastic manner. Then ultimate load method, which is also known as load factor method. In this method, we get the collapse or ultimate load by applying the working load with suitable load factor. Most of the part of second lecture was on limit state design. This design method is very important for design of safe and serviceable structure. Most of the structural design in this video lecture series will be based on limit state design. The aim of this method is to achieve acceptable probability that a structure will not become unfit for the use for which it is intended. To ensure the objective of limit state method, IS code recommends that the design should be based on characteristic value for material strength and applied load. Then using this characteristic value, we calculate the design value. For materials, to get the desired design strength, we divide the characteristic strength by partial safety factor. And for desired design load, also known as factored load, we multiply partial safety factor with the characteristic load. Then we learned about design stress strain curve for concrete and steel. So in previous two lectures, we have learned a lot of basic concepts that will really help us for design in upcoming lectures. In this third lecture, we will learn some important points before understanding the concept of flexural behavior of beam. In the first part of this lecture, we will learn the difference between analysis and design of structural elements. Then the importance of symbols and notation we use in designing. Then a brief view of simple bending formula, which we have already studied in strength of materials. And then transform area method for composite section. Composite section is made of two different materials like concrete and steel. And finally we will learn about stretching moment. After understanding these important points, the second part of this lecture will be on concept of flexural behavior of reinforced cement concrete beam. So before going into detail, let us first take a look at why we are studying the flexural behavior. What is the importance of concept of flexural behavior of beam in designing? Here I would like to introduce you to the meaning of word flexure. It is the act of bending. So please don't get confused if I sometimes use the word bending and some other times flexure. So let's start here. We know that the main components of any reinforced cement concrete structure are beam, slab, column and footing. The main criteria for design strength in beam and slab is bending. Main criteria mean that structural member should be designed according to most critical conditions and later should be checked for other normal conditions. So in case of beam and slab, most critical condition is bending. Hence first we will design according to bending condition, then we will check it for other conditions like shear, torsion and compression. On the other hand, for column and footing, compression as well as bending both are equally important. So you can see here that concept of bending is important in all types of structural elements. If you know the flexural behavior of beam, then it will be really helpful in making good design decisions for material strength and their section properties like their size and how much reinforced steel is required. So let's start here with the difference between analysis and design of structural elements. At this level, I hope you will be familiar with structural analysis. In the analysis problem, the cross-section dimension, concrete strength, reinforced steel area and location are already given. What you have to find out is the overall strength of structural element like stresses induced in materials and ultimate bending moments that element can resist. In design problems, design load and applied moment are already given. You have to find out the dimension of elements, the concrete strength, or we can say grade of concrete that we will use according to load and how much steel is required. When you solve the analysis problems, this give only unique answer. That's why analysis is easy, but design problems give a lot of solutions. That's why design problems are difficult as compared to analysis problems. So here you will deal with both types of problems, analysis as well as design. But most of the problems will be design problems. Next is importance of symbols and notation. We use symbols and notations to represent specific properties or characteristic values. For example, we have already used some symbols like STK for characteristic compressive strength of concrete and STR for modulus of rupture. If you look at IS 456, here on page number 11, the symbols and notation we use are already given. So these symbols and notation should be memorized because they are commonly used and discussed in design problems. You don't have to memorize all of them at the same time. Try to memorize from time to time as they will come in use in the analysis or design problems. Now move to simple bending formula. You have already studied the simple bending formula in the subject strength of material. E upon R is equal to sigma upon Y is equal to M upon I. If we apply simple uniform moment on a beam, this beam will bend uniformly and normal stresses induced in beam section. We represent them with a symbol sigma. Y is the distance of extreme fiber from neutral axis and E is the modulus of elasticity of beam. Here R is the radius of beam curve after bending and 1 upon R is called curvature of beam. It is a very important factor. We will use it in flexural theory of RCC beam. We represent it with phi. We write this formula in the form of bending stress like this. Here we know that M is applied moment and I is moment of inertia. This formula is derived for ideal condition. Sometimes we use F rather than sigma. It is based on conventional bending theory that materials we use should be homogeneous and isotropic like structural steel. But reinforced cement concrete is a composite material. It is made of two materials, concrete and steel. To solve this problem, we can use transform area method in which we can simply transform one material into another form under linear elastic range. So here we move to another important concept, transform area method. There would be a question in your mind that how it is possible to transform one section of material into another section. The concept of modular ratio make it possible. In second lecture, I have given you a brief introduction of concept of modular ratio. Modular ratio is the ratio of two moduli of elasticity. Suppose we have two materials of different modulus of elasticity, E1 and E2. So the modular of ratio for them will be M is equal to E2 upon E1. So using the concept of modular ratio, we can transform the composite section into equivalent homogeneous section of same material. Suppose we want to transform material 2 into 1. Then E2 is equal to ME1. We can replace this area of E2 with ME1. The area of transformed section may be less or more as compared to initial area. It depends on value of modular ratio. In similar way, using the concept of transformed section, we can transform the area of steel into equivalent concrete area. But in case of RCC beam, we cannot use the formula of modular ratio directly. IS code suggests a different concept of modular ratio for RCCB. We know that modular ratio in reinforced concrete is defined as the ratio of the elastic modulus of steel to that of concrete. But IS code does not consider this formula appropriate to determine the value of modular ratio, because I have told you in first lecture under the concept of modulus of elasticity of concrete that short-term modulus of elasticity EC is equal to 5000 under root FCQ. This formula is based on instantaneous load. It does not consider the long-term effect of creep. Considering the long-term effect of creep, IS code suggests the following approximate formula. M is equal to 280 upon 3 sigma CBC. Sigma CBC is permissible compressive stress of concrete in bending. Here code also helps us to find the value of sigma CBC according to grade of concrete. In this table, these all are the grade of concrete. This is the corresponding compressive bending stress, and these all are the value of modular ratio find out using the formula M is equal to 280 upon 3 sigma CBC. One more thing here is that transform area method is only applicable for linear elastic range of materials. It simply means that we can only use this concept in working stress method. I have already told you that working stress method is based on linear elastic theory. Now let's try how to use the concept of transform area method and modular ratio to transform steel into equivalent concrete area. This is the cross section of RCCB. Here AST is the area of steel in tension zone. Beam area below the neutral axis is in tension and above is in compression. Here ASC is the area of steel in compression zone. So how to convert the area of steel into equivalent concrete? For tensile steel, the area of tensile steel ASC is transformed into equivalent concrete area MASC. You can see here that the area of steel is replaced by equivalent concrete area MASC. When we replace steel, there is an empty area which is equal to the area of tensile steel. So to make it perfect, we have to subtract this area from equivalent area of concrete, or we can write it as M-1 ASC. I have explained you this concept for bending beam, but code suggests that this transformation is valid for both flexural and direct tension members. If we look at compression steel, the value of modular ratio is considered greater than that of tensile steel. Here code suggests that transform area of compression steel ASC should be taken as 1.5 MASC rather than MASC, because actual compressive stress in concrete is much larger than calculated compressive stress using elastic method. The reason is long-term effect of creep and shrinkage and non-linearity at higher strain. And I have already told you during the drawbacks of working stress method that we cannot account the creep and shrinkage effect by using working stress method. So the point is that when we use modular ratio for tension steel, it will be MASC, and for compression steel, it will be 1.5 MASC. So here we have finished 4 important concepts. Now move to cracking moment. Before talking about this concept, I would like to remind you that in first lecture, I told you about tensile strength of concrete, where you learned about modulus of rupture. On applying the load on beam section, the extreme tension fiber is expected to crack first before any other fiber. So at time of crack, stresses induced in beam reach the value of modulus of rupture FCR. The moment at first crack is known as cracking moment. MCR is equal to FCR IT over YT. Here IT is moment of area of transform section and YT is distance between neutral axis and extreme tension fiber. So here we have finished all the important concepts that will be helpful in understanding the flexural behavior of beam. Let us consider a simply supported RCC beam with only reinforced steel in tension side. We call it singly reinforced beam. This beam is loaded with gradually increasing two concentrated loads. The central segment of beam is in pure bending, so to resist the applied load, internal moment is induced in beam. If we look at the cross-section area of beam, let me export it in another slide so that you can understand it easily. Initially, let us say that applied moment is less than cracking moment MCR. So we call it uncracked section. This is the neutral axis and the area above neutral axis is in compression and below is in tension. The distance of upper fiber from neutral axis is known as XQ. This is the cross-section view of beam. The complete area is effective to resist the stresses, so we call it effective section. The area of all steel is AST. The distance between extreme fiber of tension to compression side is total depth of beam. D is breadth of beam, and the distance between centroid of reinforced steel to extreme compression fiber is known as effective depth of beam section. As we increase the moment gradually, it increases the strain and also the curvature of beam. Let me show you, this is on strain profile. Here epsilon C is strain in compression area and epsilon P is strain in tension area, and phi is curvature of beam. So as we increase the moment, it increases the strain and so the curvature of beam. To study this behavior, we can draw a moment curvature diagram. If we are not applying any load, then curvature will be 0 because the strain is 0. As I start increasing the load, moment increases, so the curvature also increases. When moment is less than cracking moment, stresses induced are less than modulus of rupture. As moment becomes equal to cracking moment, induced stresses reach to level of modulus of rupture. SCT is equal to FCR. So what happened here? There will be some discontinuity because concrete is a brittle material and it gets cracked. So we are going to draw a step for this discontinuity. And we continue to keep loading and moment increase the cracking moment. So moment continue to increase and curvature diagram also increases. And it remains linear elastic until steel starts yielding. The moment associated to yield point is known as yield moment, My. And after yielding occurs, we start seeing the plastic deformation. By moment curvature curve, at this point, graph become more horizontal. Here graph increase lightly and then concrete collapse completely. If we look around the peak height, the moment associated to this point is called ultimate moment MU. On this graph, I am going to explain you the 4 stages of concrete flexural behavior that we need to look in more detail. This linear area where nothing is cracked is uncracked phase. Then concrete gets cracked in tension. Here concrete and steel behave like linear elastic materials, and the region up to the yielding is cracked elastic section. In this section, materials also behave as linear elastic. This behavior is also known as in-service behavior or normal operation. And then final or ultimate phase or collapse phase. Here concrete collapsed completely. At this level, I have described you the concrete behavior in simple manner, but reality is that each of these 4 stages require a mathematical explanation to do any sort of analysis. If you understand the analysis process, then it will be easy for you to understand the design process. And I can say you with guarantee that after understanding the analysis process, you can design a structure which will not only be safe and serviceable, but also will be more economical. Mathematical explanation will also help you to understand the difference between working stress method and limit state method. So let's first start with uncracked phase. In the early stage of loading, the applied moment is less than cracking moment, and maximum tensile stress (STT) is less than FCR. Neither steel yielded nor concrete cracks, hence both in linear elastic range. The analytical approach to solve this type of problem is to first find out the location of neutral axis. Here, entire cross-section of concrete is effective to resist the moment. In this case, you can completely ignore the reinforced steel because concrete section alone is effective to resist the tension stress. We can apply the simple bending formula to analyze the stresses. After increasing the load, you see the first crack in concrete and moment is equal to cracking moment. Here steel has still not yielded, so you can ignore it here. The analytical approach is like phase 1, but the main difference here is that slide moment is equal to cracking moment. And again you can apply simple bending formula to calculate the stresses induced. If you remember from the previous lecture that there is another way to find out the induced stresses. Do you remember? Yeah, there is a way. According to IS code, if you know the grade of concrete, then FCR is equal to 0.(FCK) gives you the value of induced stresses for these two types of phase. If you want more accurate results, then you can use transform area method. You can convert steel area into equivalent area of concrete. Now move to third phase, linear elastic crack phase. Here applied moment exceeds the cracking moment. The maximum tensile stresses in concrete exceeds the flexural tensile strength and section start to crack on tension side. And as load increases gradually, these cracks start to widen and propagate towards neutral axis. You will not be able to see these cracks, and concrete is no longer effective in tension zone to resist the tensile stresses. It may be noted that concrete in tension side is not quite useless. It serves the important function of holding the reinforcing bar in place, resisting shear and torsion, enhancing the flexural stiffness of beam and thereby reducing deflection and providing protection to steel against corrosion and fire. All the tensile stresses are taken by steel. Here steel has a very large tensile stress compared to that of concrete. The important point here is that both the materials still behave linearly. Most of the structure comes under this condition. The analytical approach for this phase is simply finding the neutral axis like in previous phases. The loads we apply here are known as service load, and stresses under service load are usually within linear elastic range. So here we can use transformed area method and can find out the equivalent stress using modular ratio. As I have told you in last lecture that modular ratio shows the relationship between stresses in steel to stresses in concrete. To find the equivalent stress, you must divide the steel stresses with modular ratio. Another way to solve this phase is force equilibrium method. That total tension force is equal to total compression force, where we can take resultant of tensile forces of steel and take resultant of compression forces of concrete. Z is lever arm between these two forces. Further, you can solve the equation of force equilibrium to find out the stresses in concrete and steel. You will understand this concept more precisely when we use it in real analysis and design problems in next lecture. Now move to final phase, the ultimate or collapse phase. Now the applied moment on beam section is increased beyond the linear elastic phase. Concrete crushes in compression. Stresses induced in steel FST is much more and more greater than yield stresses. Steel and concrete are no longer linear. Stress profile is no longer linear. According to IS code, stress profile becomes something like this. Initially parabolic, then rectangular. And stresses in steel go beyond yield stresses. And moment associated to this high peak value is known as ultimate moment. So in design problems, we use the ultimate moment as a reference to find out induced flexural stresses. The analytical approach of this phase is first find out the location of neutral axis, then use force equilibrium equation and find out the induced stresses. We cannot use transform area method here because concrete and steel are no longer linear. Now after we have finished this lecture, let us take a look what we have covered in today's lecture. Initially I explained you some important points which are really important to understand the flexural behavior of RCC beam. Then we learned about the differences between design and analysis of structural elements followed by symbols and notations. We use symbols and notations to represent specific properties and characteristic values. After that, we have learned about simple bending formula, which is derived assuming the materials to be homogeneous and isotropic, but we cannot apply this formula directly. That's why we use the concept of transform area method to transform the area of steel into equivalent concrete area. After that, we have learned about cracking moment, the moment at which first crack is induced in the tension zone of concrete. And finally, the flexural behavior of RCC beam, where I describe the four phases of beam when we apply gradually increasing load. Uncracked phase, concrete cracked phase, and third was linear elastic crack phase, and finally the ultimate or collapse phase. So in first three lectures, we have covered the properties of concrete and steel in first lecture, some more basic concepts in second lecture, and finally flexural behavior of RCC beam in this lecture. In the next lecture, we will start the actual design problem with working stress method, where we will be practically dealing with theoretical concepts learned. Till then, happy learning, keep connecting links with Nathan Link. Thank you.